Hello everyone. In previous part, we explored what electric charge is and how it appears in the physical world. Now we go a step deeper. If you'd like, you can revisit the first part to follow the full journey. To understand why charge behaves with such a precision, we turn to a deeper idea, symmetry. In physics, symmetry reflects rules that remain unchanged, and electric charge is closely tied to one such a fundamental principle. In this part, we explore how these ideas come together to shape and define charge's reality. Let's take a quick journey through how our understanding of electric charge has evolved. In the 18th and 19th centuries, scientists believed charge was kind of physical fluid. Thinkers like Benjamin Franklin imagined it as electric fire flowing through objects. If something had more of this fluid, it was positively charged, and if it had less, it was negative. Since it was treated like a fluid, they believed charge was continuous, divisible without limit. At that time, charge was simply something responsible for sparks and attraction. Today, the picture is very different. Modern physics defines charge as fundamental property of the particles, the building blocks of matter. It is not continuous but quantized, existing only in fixed, indivisible units, and it determines how matter interacts with energy and light. And that leads to one of the most important insights in physics: charge doesn't flow like fluid, it comes in discrete packets. The quantization of charge. This brings us to one of the most important features of electric charge, its quantized nature. Charge is fundamentally quantized. It exists only in discrete packets, not a continuous range. Every measurable charge follows the relation Q is equal to n times E, where n is an integer. This means that values like 0.5 times E or zero point 0.1 times E are not observed under normal conditions. This principle was confirmed experimentally by Robert Millikan through the oil drop experiment. In this experiment, tiny oil drops were suspended between the electrically charged plates. By precisely adjusting the electric field, Millikan balanced gravitational and electric forces on each droplet. By measuring the charge on many droplets, he found a striking pattern. Every charge value was an exact multiple of smallest fundamental unit E, which is equal to 1.6 into 10 raised to minus 19 coulomb. No intermediate or fractional values appeared. This provided direct and convincing evidence that charge is discrete, not continuous. However, this leads to a deeper question. If E is the smallest unit, what about quarks? Quarks actually carry fractional charges like positive 2 as to 3e or minus 1 by 3e. However, due to a phenomenon called confinement, quarks can never exist freely. They are always bound together inside particles like protons and neutrons. And when combined, their charges always add up to a whole multiples of E. So in all observables, free particles charge will still appear quantized in units of E. That's why E is called a smallest unit of charge, not because smaller fractions don't exist in theory, but because nature never lets us observe them independently. To really understand electric charge, we need to carefully pull it apart from another concept it's deeply tied to: the electromagnetic field. A field in physics is something that exists everywhere in space. It assigns a value to every point whether anything is there or not. Electromagnetic field is a perfect example. It quietly fills all of the space, defining what force would act on a charged particle if one were placed at any location. Charge, however, is something entirely different. Charge is not spread out like a field. It does not exist everywhere. It is a property carried by particles like electrons or protons. It tells us how strongly a particle responds to electromagnetic field and how strongly it influences that field in return. So the distinction is clear. The field describes the environment of influence, while charge determines the degree of participation in that environment. They are deeply connected, but they are not the same thing. Charge does not turn into a field, and a field is not a concentrated piece of charge. Instead, they form a relationship. The field sets the stage, and charge is what interacts with it. And here is where things become even more interesting. Just as charge is quantized, coming in a discrete packets, the electromagnetic field at a deeper level is also quantized. In the framework of quantum physics, the field is not perfectly smooth and continuous. Its energy is exchanged in tiny discrete units. These units are what we call photons, the fundamental quanta of electromagnetic field. So while the field appears continuous on large scale, at its core it has a subtle granular structure. Universe where discrete charges interact through a field that is itself quantized at its core, together shaping the behavior of physical reality in a way that is far richer than either idea alone. Now that we have separated charge from field, we can ask a more meaningful question: what does charge actually do? At its core, charge is about interaction. It determines how a particle responds to electromagnetic field, and just as importantly, how it shapes that field for everything around it. When a charged particle exists, it doesn't sit passively. It modifies the space around it, creating a structure in the field. And this structure that gives rise to what we observe as forces, motion, and energy transfer. So, in a very real sense, we never observe charge directly. What we see are its consequences: attraction and repulsion, the motion of particles, the behavior of matter under electromagnetic influence. Charge, therefore, is not merely a property, it is defining parameter of interaction. It governs how particles influence one another within the electromagnetic framework. In the absence of charge, there would be no mechanism for electromagnetic forces, no binding of atoms, and no structured electromagnetic behavior. In this way, charge plays a fundamental role in determining how physical systems interact and evolve. To move closer to a fundamental origin of electric charge, I now turn to a deeper concept from modern physics: symmetry. In quantum theory, particles such as electrons are described by wave functions, which include a quantity known as phase. Although this phase is not directly observable, it is fundamental to how the theory is constructed and how physical predictions are made. A key insight is that if I change this phase uniformly everywhere, the physical outcome remains unchanged. Nothing measurable is affected. This invariance reveals the presence of the symmetry in the laws of physics. This symmetry is known as Gauss symmetry. It expresses a powerful idea: the fundamental laws should remain unchanged under certain transformations of our mathematical description. However, the situation becomes more subtle when I allow the phase to vary from point to point in space. In this case, the equation no longer remains consistent. The derivative introduces an additional term, causing the result to depend on arbitrary phase choices rather than physical quantities. To restore the consistency, I do not simply adjust the equations, I redefine how change itself is measured. I replace the ordinary derivative with a new form. The covariant derivative is the partial derivative plus the Gauge coupling term IQ mu. This modified derivative introduces a field A mu, which corresponds to electromagnetic field. The constant Q determines how strongly the particle interacts with this field, and this interaction strength is what we identified as an electric charge. What is remarkable here is that charge is not introduced arbitrarily, it emerges naturally from the requirement that the symmetry must hold at every point in space. Finally, through another theorem, this symmetry leads directly to a conservation law: electric charge is conserved. This reveals a deeper conclusion. Symmetry is not just a feature of our equations, it is a principle that shapes the very structure of our physical reality. We can now bring these ideas together into a deeper understanding of electric charge. To preserve the Gauss symmetry consistently across a space, nature requires the existence of the electromagnetic field. It is not introduced arbitrarily but emerges as a direct consequence of the symmetry itself. Within this framework, charge is not substance or a fragment of a field. Instead, it is a fundamental parameter that determines how strongly particle interacts with the electromagnetic field. In its most refined sense, charge is simply a number, one that arises from underlying symmetry of nature and governs interaction at the most basic level. From the phase perspective, it reflects how particles' quantum wave function responds to a phase rotation. A positive charge corresponds to a phase that shifts in one direction under interaction with the field, while the negative charge shifts in the opposite direction because of the opposite response. The particles with like charges repel, while the opposite charges attract. They are coupling to the same field but in fundamentally opposite ways. Neutral systems, on the other hand, show no net phase response, either because they carry no charge or because opposing contributions cancel out. Most importantly, charge is invariant no matter how a particle moves. Even as it approaches the speed of light, its charge remains exactly the same, reinforcing its role as a fundamental and unchanging property of physical reality. To conclude, we have moved from early intuition ideas of charge as flowing substance to a modern understanding rooted in quantum theory and symmetry. We have seen that charge is not a material entity but a fundamental property, one that governs interaction, emerges from symmetry, and remains conserved across all physical processes. But at deepest level, these ideas are not truly understood through words alone. They are understood through mathematics. It is the mathematics that gives the precision to quantization, that defines how charge interacts with fields, and that reveals symmetry as a fundamental principle rather than just an abstract concept. Without mathematics, these ideas remain descriptive. With mathematics, they become exact, predictive, and deeply connected. Thank you for your kind attention. Stay curious.